Good evening, my dear warriors. Do let me know quickly in the chat box if I'm audible and visible to all of you. Yes, I'm going live from the Bangalore studios, so I might look a little different, and yeah, maybe I might be little bit nervous while using this board because I'm used to my home studio. Let me know if I'm audible and visible, and have you marked your attendance already? Yes, my dear warriors. Done, dusted. Perfecto, perfecto. Let's begin with the lecture. Yes, your Captain Shreyas is live for all your JEE 2026 aspirants, whether class 12th or the droppers. And we are on to the magnetic sources, Ampere's law and its applications, where we are going to see all the important formulas like for an infinitely long wire, for a sheet carrying current, solenoid, toroids, and even inside the wire, the magnetic field, and all the applications and the PYQs and all of this in today's lecture. So quickly, let me know in the chat box if you are ready, geared up with your Captain Shreyas, your physics master teacher who has been guiding your seniors for the last 13 plus years, sending them into IITs, NITs, IIITs, and all the important tier 1, tier 2 colleges in the country. Now it's your turn. Yes, Adarsh, Sudura, Karthika, welcome Ardachala, welcome Amina, hello Harshita, hello everyone, nice to see all of you out here, welcome, welcome, chat box to be lit. Yes, so last lecture we have already seen the Bio-Savart's law and its application. So today Ampere's law, and let me remind you, if you want lectures just like this, in fact on the platform, in a very scheduled manner with class tests, and you want our personal mentorship, your Namrata ma'am, Diksha ma'am, your PNJ sir, me, and your all your favorite master teachers out there in a dedicated batch in pure English with entire 11th and 12th standard syllabus, along with the study material, mock tests, all India level tests, and assignments and DPPs, along with doubt solving within the class. You have the Sigma batch. It just started yesterday, so please check out the link which is there in the description box. All amazing features at an affordable price, and also you can get the books and the revision flashcards, everything couriered at your doorstep. Okay, so check out the combo pack as well as the regular prime version. Both of them, link is there in the description box. Yes, Theory of Science, no Vedantu t-shirt. Don't complain, man. Yeah, sometimes you kids also go, no, ma'am, sir, my uniform, gone for washing, this, that, right? How are you, sir? Too long. Am I long? Like, oh, long time. I thought I was looking long. Okay. Good evening, Hattrick here. Okay. Yes. Good evening. Good evening, Ibu. Good evening. Ibu is our Sigma batch student. Hi, Arsita. Yes, let's begin. So, starting off with Ampere's law. Do you remember Gauss law in electrostatics? Do you also remember Coulomb's law in electrostatics? Do you know what was Gauss law doing with respect to the Coulomb's law? Well, if there are point charges, easily through Coulomb's law, you can find out the electric field. Gauss law was a better version where you have symmetric bodies like shells, spheres, sheets, wires, etc., which can be then, you can conveniently find the electric field using Gauss law. So it is an alternative for Coulomb's law, but for symmetrical bodies. Isn't it correct? Yeah. So, my dear warriors, same way, Bio-Savart's law tells you due to a current carrying element what is the magnetic field. But for some symmetrical bodies, we can use Ampere's law to find the answer very quickly by using this property. So it is an alternative to your Bio-Savart's law. So it's an alternative to your Bio-Savart's law, and preferably used for symmetrical bodies. It is preferably used for the symmetrical geometries. Now, if you remember, in Gauss's law, you used to take the dot product of the area vector with the field vector, and you used to do a cyclic or a closed surface integral. Do you remember that? You used to have the field vector and you used to do the dot product with the area vector and you used to integrate it, and this quantity was called as the flux, if you remember. Here we have the magnetic field and we do not find the integration with respect to the area, rather the length, and we have something called as the closed line integral. But before talking about closed line integral, so let's talk about the line integral. Let's talk about the line integral of field, line integral of field. So say for example, I travel from one point to the other and I'm going like this, from one point to the other. At every single point there could be some magnetic field, maybe like this, maybe like this, maybe like this, maybe like this, maybe like this. These are the magnetic fields at different points. I choose some random point where the magnetic field is B, and at that point I move a small distance called as dl. dl is a small distance which I have moved along that particular path. So the line integral of the field means you take the dot product of the magnetic field, you take the dot product of the magnetic field with the distance traveled, and you basically integrate it from first point to the last point, or the initial point to the final point. That is called as the line integral of the field. Yeah, I hope this is absolutely clear. With the right hand thumb rule, we find the direction of magnetic field or current. Anirudh, it depends what are you using it for. I will give you the clarity, just give me a second. First let me complete this, just remind me of this doubt after this slide, or maybe after this Ampere's law, I will answer your doubt. Okay, fine. Yeah, the classes are 6 o'clock, 8 o'clock, 6 for your 11th standard and 8 o'clock for your 12th standard syllabus. Okay, but it's not like 2026 should only watch 8 o'clock class. No, 2026 students should watch both 6 o'clock and 8 o'clock class. Okay, got it? Now when I say the word closed, when I say the word closed, that means I will put this symbol, and that means I am coming back to the same point. That is the meaning of closed line integral. So if I come back to the same point, I start my journey, and as I travel, I come back to the original point. This is basically a closed path. Like you had a closed surface, this is nothing but a closed path. Like I'm going for jogging in a garden, I come back to the same point. Or I start from home, I go to school, I meet my friends, I went to a shop, I bought something and I came back to the house. It's a closed path. Such a closed path is also called as an Amperian path. It is also called as an Amperian path. If you remember, Gauss surface was a surface which is closed. Same way, an Amperian path is a path which is coming back to the same point. Okay, so that is called as an Amperian path. I hope this is absolutely clear. How is this Amperian path useful? It is useful to find the magnetic field using Ampere's law, and I will show it to you right away, right now. All right, so let's understand how it works. So in this Amperean law, what we need is maybe a bunch of wires which are carrying some currents. Maybe this is carrying some current 1, maybe this is carrying some current number 2, maybe there is another wire carrying some current number 3, maybe another wire carrying some current number 4, another wire carrying some current number 5, okay, something like that. Okay, I'm just chumma drawing some currents I0, I1, I2, I3 like that, and I start my journey, let's say from this particular point, and I start moving like this, and I go like this maybe, and then I decide, okay, after this I'm going to take a turn and I'm going to come back because I want a closed path. This Amperian loop law only works for closed paths. Please keep that in mind. So as you can see, I have come back to my original location. I have come back to my original location. So this is nothing but my Amperian path. Amperian path. Everybody with me on this? This is called as an Amperian path. Everybody able to visualize? Okay. Bhanu, yesterday I uploaded the planner for the month wise, Bhanu. A daily timetable, is that what you want? Then I will upload it separately. Yesterday only I have uploaded the month planner for the entire August to January, what you should be doing in every single month. I hope you have watched it. Okay. Now at all these points there will be some magnetic field. Okay. Achuma say, all right, there is a magnetic field like this over here. So I'll call this as magnetic field B. And as I'm traveling, I'm moving small distances. Let's say I call it dl. So if I take the closed integral, if I take the closed integral of the magnetic field, closed integral of that particular magnetic field with respect to the distance that I am traveling, the answer that I get is, compare it with Gauss law, you will find a lot of similarity. In Gauss law, the integration of field with area gave you what? Yes, the charge inside by epsilon. So here it will not be the charge, rather it will be the current which is inside or enclosed, the current which is inside, but do not divide by epsilon. Epsilon is for electricity. This is magnetism. So you will use permeability, but permeability will work exactly the opposite way of permittivity. So if permittivity in the formula comes below, permeability will come on the top. If permittivity comes on the top, permeability will come below. That's how it works, always opposite. So here I will put mu naught multiplied by the current inside. Mu naught, of course, is our permeability, whose standard value in SI unit is 4 pi into 10 to the power minus 7 SI units. This is your permeability. This is your permeability, which I have explained before. It tells you how permeable is the magnetic field inside any given medium. This is current which is enclosed. So let me block this result for you. This is nothing but your Ampere's loop law. This is nothing but your Ampere's loop or Ampere's circuital law. Yes, mu naught will be in the numerator. Yeah. Now you might be wondering, sir, what is the enclosed current here and what is the outside current here? Like as you can see over here, I naught is outside this circuit or the Amperian path. Even I phi is outside the circuit. So here I naught and I phi are outside. So you will not consider it. So technically what is inside is this. The current which is inside, is I1, I2 also, I3 also and I4. But there is a catch and you need to be careful. We need to use signs. But sir, which one is positive, which one is negative? For that, we have right hand thumb rule. And how does it work? See how you traveled. You have traveled like this. So take your right hand. The 4 fingers will travel along the path. So the 4 fingers of your right hand, will travel like this. And whichever direction your thumb will point, that will be the positive direction. That is the right hand thumb rule. So as you can see, I1 and I4 will be positive. So this will be I1 plus I4. And as you can see, I2 and I3 are opposite. It's downwards. So it will be minus I2 minus I3. So that's how the sign convention works. So you have to use nothing but the right hand thumb rule. That's it. Curl your fingers in the direction of the Amperian path. The thumb points in the assumed positive direction. Is that absolutely clear? How can a current carrying conductor produce magnetic field? Okay, JEE aspirant, I'll ask you another question. Tell me, why should a charge produce electric field? Just think about it. Yeah. Why should a mass produce gravitational field? Why should a mass attract some other mass? What is it that a charge does to other charge that it attracts and repels? You'll be like, sir, it is natural, no, mass will attract mass. Okay, sir, we see it falling. Sir, a charge will obviously repel a charge or attract a charge. So same way, a current carrying wire, okay, understand, it is actually just a source of magnetic field at the end of the day. Later on, you will learn that actually when charges move, okay, in the relativistic frame, it's basically, you can say that the magnetic field is the electric field only. You will later on realize electric and magnetic field are exactly, you know, co-brothers or twins, or you can say siblings. It's just a matter of perspective. When you are stationary, it looks like electric field. When you are moving, it looks like magnetic field and stuff like that. Okay, I hope this is absolutely clear. So it is like an inbuilt characteristic. I hope this is absolutely understood. Yeah. Now, having said this, sir, I have a doubt in magnetism matter, application of bending and magnets. Yeah, it is important. Abhiram, you might get a question on this. Now, having said this, sir, you know, I have this doubt of when to use curled fingers for current, when to use curled fingers for magnetic field. See, go by logic. I mean, see, if you have a straight wire which carries current versus a coil which carries current, here, when you have a straight wire which carries current, the magnetic field lines are basically circular. Here, also they are curved, but the magnetic field will come like this and then it will go like this. Isn't it? This is how the magnetic field lines will look like. See what is turning here, what is rotating, what is circular? The magnetic field. So obviously your curled fingers will be magnetic field, current will be the straight wire. Here, what is turning, what is rotating? Current. So current will be the curled fingers and the magnetic field will be the thumb. So don't remember like magnetic field is always the thumb or magnetic field is always the curled fingers. No, go with the flow. See the geometry. Whatever is rotating is curled, whatever is straight is the thumb. Is that now clear, everyone? Yeah. Anirudh, I think that was your doubt. Yeah. JEE Aspirant, I hope your doubt is clear. Abhiram, I hope your doubt is also cleared. Chaziran Kudun, welcome my dear warriors. And how can electric field and magnetic field have same properties like the magnetic field while electric? Yeah, that is what is very interesting, JEE Aspirant. Let me also tell you, JEE Aspirant, that electric field can also be in a closed loop. If somebody told you electric field can never be in a closed loop, that is wrong. We will see that in EMI chapter, even electric field can become a closed loop path. Yeah, closed loop path. Yeah. Yeah. Hi Sai, welcome aboard. Yeah. Right. So there is nothing like, you know, electric field can't be closed loop path. It can be a closed loop path. It's crazy. Yeah. So to think about it. Now, the reason why magnetic field happens to be always a closed loop path but never an open loop path is because you can never ever separate out the poles. You can never ever separate out, you know, the positive polarities and the negative polarities, but with electricity you can do that. Rather, I would say electric charge is more fundamental than magnetism, because at the end of the day the magnetic properties do arise because of the electric properties. So what happens at the atomic molecular level is that the atoms have those charges, the electrons which are revolving, spinning. So those spinning and rotating charges is what creates the aura or the perception or, you know, the feeling of magnetism. So the tiny molecules and the atoms and the electrons themselves have polarities north south. So it starts at the molecular, atomic, subatomic level. I hope this is clear. Yes, Ibu, I know the camera is slightly different. I mean, it's, yeah, not my studio. My studio, I always love it somehow. Okay, cool. Is this all clear? Ampere's loop law. One thing though, this magnetic field, is it due to the inside or due to the outside? Answer it in the chat box. I am reading your chats. This magnetic field, is it due to the inside currents or is it due to the outside currents? Please remember, this magnetic field is not just because of inside but also because of outside currents. So that is something which you need to understand. So the magnetic field here in this formula is due to both in and out currents, both inside and outside currents. But it is the integration which only depends on the inside currents. Keep that in mind. So it's very funny. The LHS has a term which is dependent on, because this current will create a field here. This will also, this. So this B is actually the net magnetic field of all the currents magnetic field. Each current will produce magnetic fields in some directions. You add them vectorially, it is the resultant. How can you say this current cannot produce this magnetic field? And what has this loop got to do that this magnetic field will not be due to I naught or I phi or whatever? This is just an imagination. Remember that? This is not a physical path. It's just an imaginary path. If I stop imagining, this blue line will not be there, and you will just see all the wires, and you will be like, yeah, every wire is producing a magnetic field over here. So it is the field due to every single thing out there. Got it? So another important thing which you should be aware of. Great. Now let me apply Ampere's loop law for a long wire which is carrying current. For a long wire which is carrying current, remember last time I told you it has to be done by integration using Biot-Savart's law with some crazy substitution and then resubstitution and using trigonometric integration. It's like a long method. I mean, it will take your entire JEE physics paper time. But using Ampere's law, it is very straightforward. So we have the current carrying current carrying straight wire. It's a long wire, infinitely long wire. So it's an infinitely long wire. And we know the magnetic field lines will be circular in nature. And I want to figure out what is the strength of this particular magnetic field. So what I do, I play it smart. I go exactly along the magnetic field lines. I go exactly along the magnetic field lines. So at every single place, my distance which I travel and the magnetic field, both are going to be parallel to each other. Both are going to be parallel to each other. Okay. So on the left hand side, I have the magnetic field which is dot producted with the length, and then I do integration cyclic to get the enclosed current, which is mu naught into current enclosed over here. Right hand side, I clearly can see if I curl my fingers, the thumb goes up, which is in the direction of the current. So that current is obviously positive. Okay, fair enough. Now what will be B dot dl? Observe carefully, the angle between them is 0. So it will be B into dl, B into dl into cos of 0. Cos of 0 because everywhere B and dl are parallel. Okay. I'm so glad, Karunya, you are coming here to learn what you did in 12th and now already in the 3rd year. That's a long time. I'm so glad to see you coming over here to say hi to your juniors and to your teachers out here. So glad. I hope you do really well and get placed really soon. Yeah. So I'm not putting any cap or anything because unit vector not needed. I'm just saying B dot dl. There is no cap anywhere. Oh, this is not I cap j cap. This is current. Don't get confused. Okay. So don't get confused. This is not ijk, that unit vector. This is just current, that I over here. All right. Be careful. Now keep in mind magnetic field on this entire loop is constant. So that being a constant, I can just choose it to be outside, and I will be just left with the integration of dl. Remember, cos 0 is 1. Okay, fair enough. This will be mu naught into current. Okay, next step also I'll put mu naught into current. I also have magnetic field. Can you think and tell me what is integration of dl? dl. I come back. It's a circle. So it's the length of that circle, which is the perimeter of a circle. And the perimeter of a circle, what is it? Yes, quickly tell me. It is 2 pi distance from the center, which is the radius 2 pi r. I hope this is absolutely clear. Yeah, very nice, very nice. So what do we do now? Oh my god, my leg got entangled in these wires. That's why I love my wireless mic. Like, I'm struggling now over here because I'm not so used to these wired mics. And yeah, anyways, coming back over here, just shift it and you will definitely get your magnetic field. So the magnetic field will be mu naught divided by 2 pi, and we have current divided by R. Do remember, this was exactly the same formula what we got. This is exactly the same formula what we got via integration. The surprising part is, although there is integral symbol here, but we didn't really integrate. So that is the irony of this law or this theorem. Even though there is integration, we don't really integrate. In fact, it is used to avoid the integration. So they say, right, don't judge a book by its cover. This is exactly like this. The book's cover is so scary. I mean, sir, cyclic integration, it will be scary, sir. But that's the funny part. When you actually do it, many things just come outside. The dot product, cos 0, cos 90, either it will be 1 or 0 most of the times. And a simple integration like this, which is very doable, and you get the answer within few steps. Yeah. Yes. Okay. Sir, I used cap as a short form for, oh my God. This is such a, I would say, oops moment. I thought you were saying cap for cap, but yeah, cap 2. That's why I have a special name, cap 2, not cap. Cool, got it. Oh, is it? My expressions are so visible, huh? That is very bad. I thought I can hide my emotions, but looks like my emotions are all out there. Kids know already that Shreyas Sir is unhappy with teaching over here. Okay. Now, as an extension to this problem, how about doing this question where, imagine this is a wire carrying current. This pen is like a wire carrying current. Even inside the wire, there is a magnetic field. Okay. Yes. Bhanu, just go with the flow of the Sigma batch or whatever we are doing on YouTube. You will complete anyways everything by October and November. You see, that is the best part about Vedantu JEE English. I am telling you, don't break your head. Forget everything. Whatever I am teaching, whatever maths, chemistry is being taught, just follow everything done by October, November. You don't have to break your head, right? And best part is Sigma batch, where you don't have to break your head even more because tests, assignment, everything, mentorship, everything is happening there. Cool? All right. Now, this is a cylindrical wire, and inside this there is magnetic field. I want to know inside this wire how much is the magnetic field. So this wire has been now zoomed in, so you can see the thickness and gauge a diameter, some radius is there. And if you look at the top view of this wire, it looks something like this. The current is coming out of the plane. Now, here is the catch. See guys, I want to figure out the magnetic field inside that wire. So maybe if I go inside that wire, the magnetic field lines are like this. Okay. And maybe it is at some distance of R. Maybe it is at some distance of R from the center, and at any particular location, this is the magnetic field. This is the magnetic field. I will do a smart move. I will exactly travel along the magnetic field line. I will travel exactly along the magnetic field line. So my dl vector will be exactly like this. So my Amperian path is along the loop. My Amperian path is exactly along the loop. Okay, so let's see what exactly will happen over here. We have dot dl, we have our magnetic field, we have of course our cyclic integration, which is going to be equal to permeability into I enclosed or I inside. This is our Ampere's law. Let's apply it one by one. Well, mu naught is as it is. I enclosed is not so straightforward, let me tell you. But I know one thing, magnetic field and the dl both are parallel to each other. So I will just get dl into cos of 0. Do you understand why cos of 0 is coming? Because the angle between them is a big fat 0, guys. And again, magnetic field is a constant along that loop. So being a constant, I can bring it outside the integration, and over here I'm just left with integration of dl. Sir, what is the integration of dl? But sir, you are deliberately not writing the right hand side. I think I know why. Do you really know why I'm not writing the right hand side? Is that phi variable? Where is that phi? I can't see the phi. There is no phi. This is cyclic integration, guys. Don't get confused. This is cyclic integration. Where did it go? This closed line integral means you put a circle on the integration. This is not phi. Phi symbol is this. No, this is not phi. This is integral symbol. Okay, don't get confused. It's not some variable phi. All right. Do you understand why the I enclosed is not really I, it is something else? Okay, go back a little bit, you will really understand it. See, this is my Amperian path. So technically speaking, the enclosed current is this much. This is enclosed current. Whatever current is there inside of this is I enclosed, or I which is inside. But strictly speaking, the current is actually going throughout the cross section. Oh, what to do now, sir? Hold on. I mean, current will be flowing uniformly. So if that is the case, the density of the current will be the same. So that is the crux of the problem here. The current is distributed uniformly. So which means the current density is the same. And density of the current is the current by area. So if I take this blue area, the current is I enclosed, area is pi small r square. But if I take the whole cylinder, the total current is I and the total area is pi big R square. What is R? The whole big radius of the cylinder. Is this clear, my dear warriors? This relationship, let me know quickly in the chat box. Everybody with me now? Yeah. Sir, why can't we use another shapes like a square? Yes, you can use, but always choose a shape where the integration becomes simpler. Expression should become simpler. Oh, so what is I? Capital R square. R will cancel. So I will definitely get now the magnetic field. Observe it carefully. Mu naught is there. Divided by 2 pi is also there. This R got cancelled. So current into small r, whole thing divided by just the R square. So this is the formula for magnetic field inside that particular wire. It is mu naught by 2 pi. Instead of I by R, observe this, instead of I by R, now it is IR by R square. Dimensionally, length is always there below, because length and length square will cancel, you will have length below. Is that absolutely clear? Perfect. So E Sidhu, we are choosing circle because the integration becomes easy, because the dot product now becomes of parallel vectors, and either try to keep the vectors parallel or perpendicular. When it is perpendicular, dot product is 0. When it is parallel, it is just the product of their magnitudes. There is nothing else. Okay, cos 0 or cos 180 will be 1 or minus 1. Okay. So, sir, if I actually draw a graph outside versus inside, how will it look like? It will look something like this. Because the moment you are inside, it was mu naught by 2 pi, current is there divided by R square into R. So essentially your graph is proportional to R. But the moment you go outside, it becomes mu naught by 2 pi, you have I divided by R, that means it is now inversely proportional to R. So that is why it is a straight line and then an inverse line, and the crossover or the change of graph exactly happens at R, which is the radius. So initially increases and then inversely decreases, just like the electricity graph for a uniformly charged solid sphere. Yeah, I hope this is absolutely clear. Wow, adventure boys, you guys are very smart, man. Sir, will the price of the Sigma batch reduce on the Independence Day? If you are following Vedantu for a long time, you know definitely there is some surprise coming. I can't tell you what it is, but adventure boys, whatever you have guessed is absolutely on the right side. Okay, so if you want to wait, please wait, definitely. All right, so moving on to show you a proof that this same question came. Just look at this. In 2025-24 Jan attempt, current is uniformly distributed. The graph of the field versus the distance from the center, I mean it will be a straight line, then a curved line. So exactly what I just showed you, option number B. Yeah, yes, adventure boys, it will man, it will definitely reduce. So I would say wait for it and maybe, you know, go for the combo version, because then you'll get the books and the flashcards also at a very affordable price. Okay, I don't know the exact details how much it will be, because I don't get to know anything like that. So yeah, when it comes, I'll definitely let you know. I don't have any information as of now, but it will definitely reduce. Okay, look at this question, 29th January. Consider a long wire carrying current. The current is distributed. Distance is basically half. No, the distance from the center of the wire's cross section at which the magnetic field inside the wire, outside the wire is half the maximum possible is how much? Okay. Now, where will the magnetic field be maximum? First, let's understand that. If you look at the graph, it is very obvious that the magnetic field is maximum exactly at the radius. So, first, let's write that down. The magnetic field is maximum at radius is equal to the outer radius. Here, outer radius is A. Okay. So, B max will be mu naught I by 2 pi into A. This is the maximum field. Now, let's talk about inside first, then we'll go outside. So, my inside field is the maximum field divided by 2. Now, that is the question. The point where the magnetic field is half the maximum. Maximum field, I already know, is mu naught I by 2 pi A. This is as it is. What is the formula for the field inside? It is mu naught divided by 2 pi IR divided by R square. Here, instead of radius square, that radius is itself A. So, A square. So, mu naught by 2 pi, mu naught by 2 pi, A will definitely get cancelled. And what will you get? R as. Think about it and tell me quickly in the chat box. A will go on the top. This 2 will remain. So, R will be A by 2. So, this is the first answer for inside. A by 2. Absolutely clear? Okay. A by 2 is there here and it is there here. So, B option and D option gets eliminated. Now, for outside, the magnetic field outside again is half the maximum magnetic field. Now, maximum magnetic field can be mu naught current by 2 pi A. 2 pi A. What is the field outside? It is mu naught I by 2 pi into R. Mu naught I, 2 pi will definitely get cancelled. And as you can see over here, yes, everything fine, right? So, R is nothing but 2 times of A, as you can see. R is 2 times of A. Yeah, if you want, I will put 1 by R is equal to 1 by 2A. Therefore, R is equal to 2 times of A. Everything else will get cancelled. So, 2A is definitely there here. So, this option A gets eliminated. So, option number C is the right answer. Got it, everyone? These kind of questions have come in JEE. So, this is again a very, very crucial topic, my dear warriors. Let's go to the next one coming up on your screen, and here it is. Okay. This says a long wire carries some current. The current is uniformly distributed. The ratio of the magnetic field at A by 2 and A from the axis of the wire. what is the ratio of the magnetic field at a distance of a by 2 and a from the axis of the wire. So when you consider this particular point a by 2, obviously it is inside because a by 2 is less than the radius of the wire. So we have to use the inside formula. So the magnetic field in the first case, mu naught by 2 pi current into the distance, which is itself a by 2, by the radius square. So it will become mu naught I by 2 2s are 4 pi a. That is inside. Now let us go to the next part, which is basically outside, I think, and a distance from the axis. So this is just on the surface. This is basically on the surface, and when you are on the surface, the magnetic field will be mu naught I divided by 2 pi a. That's it. That's the maximum possible field. So now you just have to take the ratio of this. I think the ratio of the magnetic field B1 by B2. This is 1 by 4, this is 1 by 2. I mean, now it is like very obvious. So you have 1 by 4 over here and you have 1 by 2 over here. Mu naught, I, a, pi, everything is the same. So this will become 2 by 4, which is 1 by 2. So it will be in the ratio of 1:2. I think the ratio of the magnetic field at a by 2 and a from the axis of the wire. I think they have made a mistake in the printing somewhere. But yeah, this answer should be 1 by 2. Yes. Is this absolutely clear, my dear warriors? Yes. So as per the question, the ratio of the magnetic field at a by 2 and a distance a from the axis of the wire they have asked. Okay. So this is exactly what it should be. So there is a printing mistake, else we would have got some other answer. Now let's go to another thing, which is basically infinite sheet. Often a square is there in the denominator. Yes, a square is there in the denominator, but do not forget this a and this a just got cancelled. This a and this a just got cancelled. So only a single a is remaining. This 2 with this 2 will be 4. Okay. Yeah. All right. Cool. Imu, Aniruddha. Sir, first should be greater than the next. So I guessed a. Oh, no, nothing like that. All right. Moving on. Magnetic field due to an infinite sheet. Now what is this exactly? See, I'll tell you what. Imagine a long, infinitely long sheet of wire like this. There are many wires along that plane like this, aligned. This is a sheet of wires carrying currents. This is a sheet of wires carrying currents. Each line is a wire which carries some current in one direction like this, and it's a sheet of wires. A sheet of a long sheet of a long wires produces a good amount of magnetic field around it. So what will it be? See, I'll tell you how to find this. Imagine you just took one wire carrying current. Then the magnetic field around it will be basically like this. Okay, this is just due to one wire. Now you take two wires carrying current adjacent to each other. Then the magnetic fields around it will be lightly like this, and they will slightly get distorted like this. This is how the magnetic field lines will look like for two wires adjacent to each other. Remember, this wire is coming in and out of the plane of the board, so it is circular. Yeah, for two wires also it is circular close by, but as you go far away, then both the fields will start, contributing, and you will see a distorted field like this. Looks like an alien's eyes. Now imagine you have three wires or four wires adjacent to each other. Just imagine three wires adjacent to each other. How will the magnetic field lines look like? Very close, only that current will affect it, but as you go far away, I think it will be somewhat like this. Oops. Like this. So now imagine there are many wires closely packed to each other. Forget the very close ones, but otherwise it will look something like this. Yeah, there will be small undulations, some small curviness which is there, but more or less it will be like this. Can you visualize it? For many wires around it, the field will be like that. Now imagine the wires are very close to each other and there are many such wires. So due to this sheet, can you now guess what kind of magnetic field will be there? 100% you would have guessed it by now. Yes, some magnetic field lines will be going like this from the top. Finally, they will come back from there, and from below, they will come like this. From below, they will come like this. So I'm not showing it completely because some of it are not visible to me. Okay, they are below me. So this is below me. Is this absolutely clear, my dear warriors? So the magnetic field lines will be above it and below it. So this will be below, there will be some magnetic field lines below, and there will be some magnetic field lines above it. But what is the important characteristic that you see? Perfectly, many of you saw it already. Yes, the undulations, the curviness will slowly go as the spacing will reduce and there are infinitely large wires and long wires. These field lines will be uniform in nature. Uniform field lines. Uniform field lines, assuming you have large sheet, long wires, large sheet, then you will see uniformly spaced field lines. Yeah, absolutely clear. So we get uniform magnetic field. How much will be the magnetic field, sir? Very easy to figure it out. So for that, take the cross section. So each of these crosses represents what? It represents a current carrying wire. Many such current carrying wires are there. What you need in such cases is a quantity, a term called as, if you go 1 unit length, how many current wires or how much current is flowing through it. So we have a term called as lambda, which is the current flowing per unit length. This is called as your linear current density. This is your linear current density, not the usual density which is per area. This is linear per unit length. Amperes per meter. In a meter, how many amperes is flowing? That is lambda. Sometimes they give K. Okay. Now, as you can see over here, if I take an Amperian path like this, as you can see, it is a rectangular one. You might be wondering, sir, why did you take rectangle now? You should be able to think why sir has taken rectangle, because below it the magnetic field lines are in this direction, above it the magnetic field lines are in this direction. So sir, what happens exactly when you take a rectangle? See, this and this are parallel, this and this are parallel, this and this and this, or this and this are perpendicular. Always my field should be perpendicular or parallel to the length to make the integration easy. Oh, that is the logic, huh, sir? Correct, bro. So B vector dot my dl vector integration cyclic will be nothing but mu naught enclosed, current enclosed. Okay. Now this integration is going to split into 4 parts, from here to here, here to here, here to here, and here to here. So there are some points which have been labeled P, Q, R, and S. So I will just integrate this. Now cyclic will split into 4. One is for P, then plus Q, and then plus for R, and plus for S. This whole thing will be equal to mu naught into I enclosed. Now notice what will happen at every single place. Okay, at every single place from P to Q, starting from P to Q, as you can see, B and dl vector are parallel, so it will be just nothing but B dl cos 0. It will be just B into dl cos 0. From Q to R, starting with Q to R, you can see B vector and L vector are perpendicular to each other. So here if I put also B, and it will be dl cos 90, which is also the same thing from S to P. From S to P, dl and B vector anywhere is perpendicular. So dl, and you will have cos of 90 degrees. O. But what about R? From R to S, B and DL vector are parallel to each other. So B into DL into cos of 0. So what happens is, this guy will completely become 0 because cos 90 is 0. This will also become 0. And at this place, magnetic field will come outside. This place also field will come outside. So we will have B and then integral of DL. Same thing over here also, cos 0 being 1, integral of DL, and you will again have B over here, and adding both of them, you are just going to get mu naught into the enclosed current. Now, how much will the enclosed current be? That logic, I will get it from here. Current I is there for L meters. So, assuming this is L meters, so this current will be lambda multiplied by the length. Lambda multiplied by the length, where length is this much. This is the length. Current per meter multiplied by the length will give me the enclosed current. Everyone? Yes. So now, what is integration of DL? By the way, this has come 2 times, so I'll put 2 over here, B. Okay. Integral of DL. Integral of DL, not the entire thing, from here to here is basically the length L itself. So I'll just put L, but as you can clearly see over here, this length and this length just got cancelled, and I'm just left with the magnetic field is mu naught lambda by 2. Now, sir, can I remember this formula? Of course. Is there an easy way to remember? Of course. Do you remember for a charge sheet in electrostatics, the electric field was sigma by 2 epsilon? The electric field due to a charge sheet was sigma by 2 epsilon. So instead of sigma, what has come? Lambda. Instead of charge per unit area, current per unit length has come. Instead of epsilon, mu naught has come, but epsilon was downstairs, so magnetism, it's opposite. So mu naught is upstairs. Half is here also, that there is no change. Okay, length is given as A, B, O. Fine, whatever, even if you put A boss, A and A will get cancelled, doesn't matter. Okay, so I will erase this. I think I didn't see that over here while solving. I'll just erase it. I was too much involved in the derivation, I guess, on my own. Okay, cool. Yes, that is the answer. Mu naught lambda by 2. Direction, how will you get? Right hand rule. How? If the current is going inside, just check it out. If the current is going inside, then the fingers will turn like this. If the current is coming towards you, the fingers will go like this. So on the top it will be left, on below it will be towards the right. So just use right hand thumb rule on any one wire. You will immediately understand above and below directions will always be opposite. Always be opposite. I think we have a question like that over here. Let's figure it out. 2 large sheets are there, and the question is, how will the magnetic field be at that particular point P? Okay, let's solve this one by one. Let's consider the top sheet over here. The currents are coming towards me. So hold the thumb towards me. You will immediately see the magnetic field will go like this and will go like this. Thumb towards me, on the top goes like that and below goes this way. Perfect. Now consider the bottom one. The current is going away from me. So the thumb goes inside. So as you can see, the fingers are curling like this. So my magnetic field will go like that and like this. So if you consider our point which is here, the point which is here, due to this sheet it is this side, due to this sheet it is this side. So for that particular point P, the upper sheet is giving a field here of the same value, lambda mu naught by 2, and the lower sheet is also giving lambda mu naught by 2. So they will both cancel out each other, and the net magnetic field at P will be a big fat 0. They will end up cancelling. How many of you understood this? Use the right hand thumb rule, nothing more, nothing less. Clearo, Amazingo, Ibu, Sidhu, Anirudh, everyone out there, right? So usually sheet questions do not come, but if it comes, now you know. Now let's go to the final part, which is solenoid and a toroid. Very simple, very straightforward. Solenoid is also used in EMI chapter as an inductor. It's a very useful device. Okay, we'll see the uses in inductor chapter EMI. But for now, solenoid is nothing but a coil which is wound, but in different planes, not in the same plane, in adjacent planes. Tuck, 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 like that. On a cylinder, you wind it. So this is the schematic diagram. You show a wire and you wind it. So there will be, current flowing through it. That current will produce a magnetic field. The current will produce a magnetic field. The funny part is, if the solenoid is long enough, then you will see that for a long solenoid only, the magnetic field inside the solenoid will be almost constant, or basically uniform. They will be basically uniform in nature, because the lines will be parallel inside of it. Yes, this is like an electromagnet, correct? So that current will produce north and south polarities. It's an electromagnet at the end of the day, correct? So the magnetic field inside is almost parallel. So inside it, it is uniform. But outside, it scatters everywhere. It's no longer concentrated. So the closer the field lines, stronger it is. Farther the field lines, weaker it is. As you can see, the field lines get scattered everywhere in the infinite volume of space. So outside, you will see the magnetic field is 0. Magnetic field outside a long solenoid is 0. Okay, this is very, very important. Everyone with me? This is very, very important, guys. Clear? Understood? Can we move ahead? Yes. Now, how much is that magnetic field? The derivation is exactly similar like a sheet. You take the cross section. Imagine this is a cylinder. You visualize, don't physically cut, you visualize a cross cut. So you will see a semicircle here. Just imagine this cut over here. So you will just see that semicircle, okay, like this over here. This is what you have to visualize. Then you will notice some currents are coming towards you from the top, and then they are going inside. They will go behind in that semicircle and come out. And every place currents are going in, coming out, going in, coming out. So we now define a new parameter over here, which is now called small n, which is capital N by N, which is the number of the turns per unit length. That tells me how tight the winding is. If there is a lot of space, there are very few turns per unit length. If the windings are close enough, there are too many turns in a unit length. Very tightly wound solenoid, whereas a loosely wound solenoid, okay, versus tightly versus loosely. So this small n is that parameter which tells me how many turns are there per unit length. I will need that in that calculation. Now again, start off with your Ampere's law, okay. Mu naught into I enclosed is there over here. We have our cyclic integration. We also have our magnetic field, and we have to do the dot product with the length vector. Okay, so let's see what exactly will happen now. Okay, I think I will be breaking it into many places, many paths. I will again choose a rectangular path. Why? Because I already know the magnetic field inside is parallel. So imagine I start traveling like this, like this, like this, and like this. So I travel like this, I travel like this, and like this, and I come back. Whereas I know the magnetic field inside of it is like this. Outside it is not there. Be careful about it. Here it is there because this is inside. This is inside. But do not forget, the magnetic field outside is 0. This is the crux in getting the final answer. Outside it is negligible. It's not exactly 0. That's why I put approximately symbol. It's almost as good as 0. Oh, okay. So what, sir, now? See, I'm going to split this integral into 4 parts. I'm going to split this integral into 4 parts. How? From, let's say, A to B, B to C, C to D, and D to A. From A to B, B to C, C to D, and D to back to A. Notice what will happen in all these places. From A to B, length and B are in the same direction, so there will be a cos 0 term here. Whereas from B to C and D to A, length and magnetic field are perpendicular. So B to C, you will have cos 90 over here, and A to D or D to A also, you will have cos 90 term over here. Whereas here outside there is no magnetic field only. Oh my god. So the magnetic field only is 0. Forget about DL. Forget about DL. Okay, just forget about DL. Okay, rest everything is as it is over here. So I'll put DL and then DL and DL, and of course we'll have B also, magnetic field everywhere. This is 0, this is B. Only place it is 0 is from C to D, which is outside the solenoid. Oh, interesting. So what happens now is a very interesting thing. Cos 90 is 0. 0 into anything, 0. Cos 90, 0. Only term to exist is this, out of which B was a constant. So bring it outside the integration, and I'm just left with integration of DL from A to B. And on the right hand side, we have mu naught into I enclosed. Okay, how much is this enclosed current in this region? There are many wires. There are many wires over here. So each wire is carrying current I. So the enclosed current is the number of wires into current in each wire. What is N? It is small n into L. So small n into L into I is the enclosed current. Each wire is I. So N into L, whatever that L is. In this case, it is basically H, as you can see. So technically, I will write it as N into H and then multiplied by I. Where is that H? Right over here, as you can see. This is that H from here to here. Okay, sir. So mu enclosed is basically NHI, magnetic field over here as it is. What is integral DL from A to B? Integral DL from A to B, DL, if you add it, we will just get nothing but the height. All right. I hope this is clear. All right. So we are just going to get H over here. Best part, H will cancel, and I am left with mu naught Ni. So that is the formula of magnetic field due to a solenoid. Mu naught Ni. Is this absolutely clear? Perfect. Perfect. Absolutely clear. Now I'll tell you one more interesting thing over here. Although the derivation we are not doing. Yes, inside the field is uniform, outside the field is 0. But keep in mind, if you are near the ends, then the magnetic field is half of that of inside. So when you are near the end, the magnetic field near the end of the solenoid is mu naught Ni by 2. Yes, mu naught Ni by 2 is there, half of what is there inside, because as you can see, they slowly start to spread out, which makes it slightly weaker than it is inside. So this is another thing which you should know. Okay. Now let's turn a solenoid into toroid. Sir, I'm in pro batch, but I need the sigma batch for organic chemistry, and you want Paul sir, of course. So what portion is going? I'm not really sure, bro. I will have to ask sir. Just leave a comment, no? Adventure boys. I will ask Pahul sir and I will let you know. Okay, because organic and physical both are running in parallel as far as I know. So organic is being taught, yeah, by sir. Oh, Ibu is already there here. Oh, Ibu can tell. GOC started yesterday. Oh, that's a good start then, Ibu. I mean, then it's a perfect time, Adventure Boys, to be in the Sigma batch. Okay. Now my question is, toroid. What is this toroid? Imagine you take the solenoid and I'm strong like Hulk and I start bending it. Zug, 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 zug. I start bending it. I bend it. I bend it. I bend it like Beckham, and I connect the open ends. It will become like a tube on which the wire is wound. That becomes a toroid. So a toroid is a solenoid which has been forcefully bent into a circular tube. Isn't it? Yeah, absolutely clear. So Ibu is in our batch, so Ibu can tell what is exactly happening in chemistry. Yes. So toroid is exactly the same. So imagine if this is the radius of the tube, and if you ask me what about the magnetic field, now the magnetic field will only be inside. Magnetic field is only going to be inside. Nothing will escape out. The magnetic field outside will be a big fat 0. And that magnetic field inside will be exactly that of solenoid, which is mu naught Ni. It will be exactly that of the solenoid, which is mu naught Ni. And if you want, number of turns per unit length is the total turns by the total length of the solenoid, which is 2 pi r. Yes. So if you open this up, the length of the solenoid will be 2 pi r. So that is the reason why I am dividing it by 2 pi r. So that is another way of looking at the magnetic field of a toroid. Is this clear? So this is the magnetic field of a toroid. Everyone? Yes? Perfecto? Okay. Right. Let's do some questions coming up on your screen right away right now. And here is the first question. Let's see if you can solve. A long solenoid, 70 turns per centimeter, per word is missing, I think. If 2 ampere is flowing, then field is how much? Magnetic field is mu naught Ni, that's it. Mu naught is 4 pi into 10 to the power minus 7. Number of turns per centimeter is given. So per meter, how much will it be? 70 into 100. Because 100 centimeters make a meter. So we have to use SI units. So if this was per centimeter, for 100 centimeters, it will be, or per 1 meter, it will be into 100. I is nothing but 2. So that's it. Put it over there and you will get the answer. Okay, pi is 22 by 7. And this 7 is also there. This 2 is also there. Minus 7 plus 1, minus 6. Plus 2 is minus 4. So this will be 10 to the power minus 4. 7, 7 cancels. 22 into 8, which is 176 into 10 to the power minus 4. Just check this out. Yes, 176 10 to the power minus 4 is the right answer. Obviously, it is in Tesla. Yep. No, it's not A. Be careful. Some of you missed something, I guess, calculation wise. So be careful. Pi was there. So 22 by 7 is the value of pi. So 7, 7 just got cancelled. Cool. If there is a solenoid that has a current which increases along the length, does the magnetic field inside stay uniform? No, it will not. It will not be uniform. It will constantly increase. Will Ampere's law not be valid? No, no. It will still be valid. It's just that we make up some approximations that outside field is approximately 0 and all of that. So you have to consider all of those things. That's all. Next is this question. A long solenoid, if the current is doubled, number of turns is halved, what will happen to the field? Oh, mu naught Ni. If it is given that the current is doubled and the number of turns is halved, 2 into half is 1. So magnetic field will be made one time. That's it. That is the answer. So 2 into half will be just 1. There will be no change at all. So the answer should be option A. Correcto. Perfect. That is the answer. And this is the last question which I will ask you to do as homework. Where will you put the answer? Answer should be there in the comment section. Sir, how will I know whether my answer is correct or wrong? Will I check other comments? Yes, please check. But also the PDF will be there after some time. So please check out the PDF link which will be there in the description box after some time. Cool guys. I hope you enjoyed today's class. Do not forget to like the video, share the video and subscribe to the channel. Next lecture will be moving on to magnetic effects, Lorentz force and all of that. That is the flow of the class. Cool. I hope you enjoyed. Bye bye. Captain Shreyas signing off. Good night.